So we don't have time to go in very detail about biomolecules. So chances are on Wednesday, I'll just pick like the amino acids, peptide, and protein, and we want to use that as an example to demonstrate how non-covalent interaction plays a role in biomolecules. But again, it depends on how today goes. If I don't have time, I don't have time. All right, so let's get started on today's lecture. So today we'll be talking about two topics. One, ring strand and structures of cycloalkanes, and then we'll spend a lot of time looking at cyclohexane, which is a special six-membered cycloalkane ring structure. Before we get started, I want to use a quick introduction to demonstrate why we want to spend so much time looking at cyclohexane. Now, cyclohexane has a molecule like it's cyclohexane, so it's a six-membered, all-carbon saturated single ring, right? So its molecular formula is C6H12, has 1 degree of unsaturation that comes from the ring itself. Now, if we look at the proton NMR of cyclohexane, this is what the proton NMR looks like at room temperature. You'll be looking at, well, it's okay, it looks like just a ring structure. I mean, all your hydrogens are equivalent to each other. What's so special about cyclohexane? Now, the thing is, if we keep on going and we look at what does the cyclohexane looks like at low temperature, then we notice some really weird things. So at low temperature, around negative 100 degrees, your proton NMR of cyclohexane would show up into two different peaks. Now, each peak is a triplet, but your cyclohexane is shown up as a different molecule. It has a different proton NMR. What does this proton NMR telling us? We have two peaks in cyclohexane. What our cyclohexane looks like, it's a six-member ring. So what this tells us is in my cyclohexane molecule, we have two different types of hydrogen atom at low temperature. Now, these two types of hydrogen might be interconverting at room temperature, and that's why I only see one peak at room temperature. So this is the point of place where the conformation of your cyclohexane actually plays a lot of role. Okay, with me so far? So I'm gonna put this experimental observation here for now. And then when we're finished talking about the conformation of cyclohexane, hopefully we can come back and rationalize what exactly is going on at low temperature of cyclohexane. Okay? Getting started, first topic here, ring strand. So what is ring strand? And how does it affect the structure of our cyclohexane? Now, as a quick review, we've been talking about hybridization of your carbon atoms with like 4 substitution around it, 4 single bond. Your carbon center is likely to be a sp3 carbon center. Now, what is the bond angle in that sp3 carbon? Anyone remember it? It's a tetrahedral, so the bond angle in between chemical bonds are expected to be something around 109.5. Right, so that is true for a molecule, like, I'm just gonna break this through, like a linear molecule. So each of these bonds, you're expecting it to be 109 degrees. So that's the expected bond angle. Now, likewise, if you have a sp2 carbon, the bond angle between these two bonds, like in ethene, are expected to be about 120 degrees. Right, so if we put it back, that's the kind of molecule we're expecting. Right, it's just about 120 degrees. What about a sp carbon? The sp carbon has a triple bond or 2 double bond around it. It is a linear molecule. So we're expecting the bond angle here to be around 180 degrees. All right? So that's a quick review. Now we know what are the bond angle we expect these carbon atoms to demonstrate what if we put it into a ring structure? Now let's use the smallest ring you can imagine, the 3-member ring. So cyclopropane. I put the cyclopropane here as well for your reference. If you have your own molecular kit or you have a visualization tool, feel free to use it. Now a cyclopropane has only like carbon-carbon single bond in between it. So if your mass is still good enough, you remember, all these bond lengths are expected to be the same. And it's a 3-member ring, it is a triangle, or in the other way to put it, it's a equilateral triangle, right? So your triangle is, all bond lengths are the same, and we're expecting the bond angle in between to be around 60 degrees. Now, this 60 degree is obviously different from what we expect for a tetrahedral carbon-carbon bond angle, right? So if we're comparing it with a linear molecule, like CH3, CH2, CH3, the bond angle here is expected to be something around 109.5. And this huge angle difference here are, in fact, one of the contributors to our ring strand, which is called angle strand. It is more complicated than that because, technically speaking, in the cyclopropane, your carbon doesn't adapt that tetrahedral geometry anymore. It's adapting a band geometry, but it's more complicated than the 14C covers. So just keep in mind, because of the ring structure, your carbon-carbon bond angle must deviate from its normal tetrahedral bond angle, and that deviation, that difference, is called the angle strand. Right, so again, what the angle strand means is the carbon-carbon-carbon bond angle in your cyclopropane is significantly different from the 109.5. So angle strand is one of the reasons cyclopropane is a very strand molecule. And when we're saying it's a strand molecule, there are several consequences of that cyclopropane being a strand molecule. One of the obvious consequences is if you imagine cleaving this carbon-carbon bond here and form the open up structure. And that process is going to be thermodynamically more favorable comparing if we're cleaving a bond in a linear molecule. All right, and the reason this cleavage is easy is because your cyclopropane is already a cyclic molecule, it is already strand. So cleaving that chemical bond will release that angle strand, will release that ring strand, and making that process a chemically more easy process. So this is one part of the angle strand. It's just comparing two different numbers, right? You're just comparing the bond angle in a cyclic structure and comparing that bond angle in its neutral molecule and make a comparison there. Now moving on, ring strand also consists a different kind of strand that is called torsional strand or eclipsing strand. We covered torsional strand before when we were talking about 1,3-butadiene and why cis 1,3-butadiene is less stable comparing to the trans 1,3-butadiene. Now this is a similar scenario. We're talking about substitutions on the cyclopropane are eclipsed with each other. So what does that mean? So if we look at our cyclopropane on the top-down view, so that's a 3D view I draw, and we're looking at from top down. And that's the wedge dash sketch you come up with. You have 3 hydrogen that's wedged out towards the camera or towards you. You have 3 hydrogen that's dashed away from you. All right, so one of the definitely technique you need in organic chemistry is imagine this molecule when you're drawing the wedge dash configuration. Like imagine it's coming out towards 3 of the hydrogen coming out towards you, 3 of them are pointing away from you. So that's the top view. But when we're flipping it to a side view, what does that tell us? Now, I'm just simply rotating this molecule here. That's our top carbon. That's the two bottom carbons. One of them is in the shadow. If we're looking at it from the Newman projection point of view, right, what we're doing is looking through the chemical bond, one of the CC bond here. And we end up getting this side view. So again, the way we're doing it is we're looking through the CC bond here, just to make it consistent to my drawing here. Right, so we're looking through one of the CC bond here. I'm holding one of the hydrogens. So if you can draw it in the Newman projection, what does that tell me? I have hydrogen, hydrogen, and on the bottom, we have two hydrogens. Now, these hydrogens are all eclipsed with each other. And to make things worse, there is one CH2 on the top. This carbon is binded to that CH2 in the back. And the bottom carbon is also bind to the CH2 in the back in the same position. So everything are eclipsed over each other in my cyclopropane. Okay? And that eclipse leads to a very unfavorable torsion strand, or putting these hydrogen groups and also these hydrogen groups on top of each other, right on top of each other. So if you remember, in a typical linear molecule, then you can have them in the staggered conformation. So let me just break it down into a linear molecule. Now, imagine now we have the linear molecule, or the cyclopropane, and you can look down one of the carbon-carbon bond here, and then in the single bond, you have free rotation. You can organize your molecule in the staggered conformation so that your different group on the carbon center can be staggered away from each other. But in the ring structure in the cyclopropane, they do not have an option. It's in the ring. They are always eclipsing each other. All right? So let me put it back to my cyclopropane. You see how stranded it is? It's really hard for me to make that three-member ring. I'm going to leave it here for you to think about it. All right? Any questions on ring strand of cyclopropane? Yes?
Is there a difference between eclipse and torsional strand?
Yes and no. So eclipse is more generally applicable whenever you have two groups that are eclipsed on top of each other. But torsional strand can be more applicable comparing to simple eclipsing on each other. Because eclipsing, we're only referring to all single bonds that are eclipsing on each other. But torsional strand, or somebody also call it steric repulsion, it might not be only with respect to the all single bonds. Okay? And just to keep in mind, in this case, we have this planar molecule. Our cyclopropane is by default a planar molecule. Right? It is 100% planar, and in this planar molecule, your hydrogen atom will always be eclipsing each other. Now let's imagine we go one carbon further, go to, I have so many models here, cyclobutane. Now this is our cyclobutane molecule. Likewise, right, I can build it in the all planar geometry. This is also a very strand molecule, cyclobutane, because the bond angle you're expected to be 90 degrees. And then 90 degrees is also diverging a lot from the typical 109.5 degrees. And at the same time, by putting your cyclobutane as a planar molecule, what we have, our hydrogen atoms are always eclipsing each other. You can see they're always on top of each other, and your chemical bonds are eclipsing each other, creating lots of torsional strand. So when we're talking about a ring strand, keep in mind, two different kinds of ring strand applies, right? One, angle strand. You look at the bond angle in that ring structure and see how different it is comparing to your on-strand molecule. and 2, eclipsing or torsional strand. Because by putting your molecule in the planar geometry, you end up having lots of eclipsing of groups in that molecule and causing the torsional strand. Now, in order to avoid those strand energy, remember we have some flexibility in the single bond. So in reality, your cyclobutane will maybe adapting a different conformation that is like, well, how do I say it? We sometimes call it puckled. So if you look at the side view, it's like twisted. It's no longer a planar molecule. So by diverging from that planar molecule, these hydrogen atoms are no longer perfectly eclipsing each other and making this conformation more stable. So that's the side view, right? So the take-home message here is your molecule might not be a planar molecule as we draw it on paper because of the conformational strand. Cyclobutane is just a quick introduction in like how likely or how unlikely these molecules are puckering each other to make it conformationally more favored. All right. Any questions before we move on to cyclohexane? Yes.
Would you also experience like the angle strain if it was like greater than 109?
Right, so the quick answer is yes, but when you have angles that's greater than 109, when you have larger rings, then those rings tend to be more flexible. When you have 8-member ring, 7-member ring, it will be much easier for people or for that ring to adapt a favored conformation. So it's not going to be a planar geometry. So do not assume your molecule to be planar if it doesn't have like lots of double bonds there to hold it a planar geometry, right? But if we look at benzene or cyclopentadiene, those are the scenario we can assume it's a planar geometry. But for all single bond cycles, when we go to 7-member ring, 8-member ring, it's unlikely to be a planar geometry anymore. All right, so cyclopropane, cyclobutane, these two are very strand molecule. And now let's look at a relatively unstrand molecule. But before we do that, again, I want you to quickly imagine cyclohexane or the 6-member ring. Like what we introduced, I don't have a planar 6-member ring built because I really just can't twist it so that it is planar. It's a little bit harder to do on a molecular kit, but I can model that on my computer. So if we imagine a perfectly planar cyclohexane molecule or 6-membered all-carbon molecule, right, cyclohexane. Now if we look at the front view, again, you have 6 hydrogen wedged out to you, 6 hydrogen dashed away from you. And if we put it on the side view, all those hydrogens will be eclipsed on top of each other. And at the same time, your bond angle here is also not the same as your tetrahedral 109.5. So that is why your cyclohexane is not going to be a planar molecule, just not going to happen. So what is the real structure of our cyclohexane? Now it's the point of view that you really need to use some imagination. This is a point of view like, if you don't see it as a chair, it's okay. I still don't see it as a chair, but you can still remember it as a chair. So this is the real conformation of cyclohexane. Let me make sure I have this one correct. Okay. Let's see. So that's our molecule. And this is a bigger version of the molecule. If you want to pass it through the room so people can play with it, please feel free to do so. I'm just going to leave it here. All right, it's the same idea. What we have is in the front, you have these groups, the carbon groups, that are going this way. And on the bottom, it's like going down. So these are the conformations we're talking about. Again, if you see it as a chair, yes. If you don't see it as a chair, also fine. But I'm just going to draw the chair conformation with you. And then we're gonna look at the Newman projection of this conformation, and hopefully it can make sense to you in your mind. So once you get the model, feel free to twist it and like feel how flexible that molecule actually feels like. Yeah, so I'm gonna pass another molecule here. That's also a chair conformation, so feel free to twist it around and see how flexible that is. And I have another one I can put in here. And the red ones are also hydrogen, but I'm just using a different color for a reason. Yeah, so pass the molecule around to the back so people can feel it. Now, if we draw this molecule on paper, how does it work? We have on the back a carbon, 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 3 carbon atom that's bending down. So it's like a bend. It's like a V shape. So it goes like this. And on the front, we have a V shape that's like curving down, curving up. Like these two are the structures we can draw. And these we connected together. Now these two bonds are perpendicular, are parallel to each other. These two bonds are parallel to each other, and these are parallel to each other. All right, so what we do, we have one V shape that's curving down, and in the front, we have a V that's curving up. And then we connect these shapes. And then on each of the carbon, you have hydrogen atoms attached to it. So these hydrogen atoms can be going up perpendicular to the internal molecular axis. So let's say this is my internal molecular axis. So if that hydrogen is parallel to that molecular axis, we draw it either up or down. So these are called our axial hydrogens, and we have our equatorial hydrogens. All right, so that's how you draw a chair conformation. And the question here is, why is this chair conformation stable? Why does the atoms want to twist themselves so the cyclohexane group becomes such a weird shaped molecule? So remember, we have two different origin of strand. One is called ring strand, the angle strand. One is called torsional strand. So angle strand comes from the bond angle deviating from your normal tetrahedral bond angle. But in cyclohexane, our bond angle here is about 111. So it's very close to your typical tetrahedral carbon center, so the angle strand is minimized. And what about the torsional strand? So in order to see the torsional strand, we can look at it from the side view. I don't know where the molecular kit is. If you happen to have it, flip it to the side view. Now let's look at the side view. Again, when we're looking at the side view, what we want to... Okay. This is a little bit bigger than I expected. Let's see. Maybe this way is better. Okay. There's lots of shading there. But if we look at the side view picture on the paper, it's the same idea. So if you have a molecule with you, like get it, play around with it, and see through the two carbon-carbon bond here. So if we go back to our original picture, what we're doing is we're flipping our molecule around, so we're seeing it through the carbon-carbon bond. All right, so we're trying to visualize what is going on along with that carbon-carbon bond there. So, right, so these are the carbon-carbon bond we draw on the sides when we draw it on picture. And now we're just looking through these carbon-carbon bond here. Okay, let's see, all right? And what we're doing is drawing the Newman projection of this molecule through those two carbon-carbon bonds. So let's do that together. It's drawing the Newman projection. We learned that before. You draw two circles, one representing the carbon here, and one representing the carbon on the right. All right, with me so far? So that's the two circles I just draw. And in the front, these are the two red dots. Those red dots representing the two carbon in the front, which are these two carbons, and two carbons in the back, likewise. Now you have, on each of these carbons, you have three groups attached to it. I mean, one is the, you have a 4 chemical bond on each of the carbon, right? One is the carbon behind it. And then on that carbon, you have one CH2 attached to it, that's in the middle, and then two hydrogens attached to it. Now let's draw that out. So that's my hydrogen, and my CH2. So this is what I'm doing right now. So these are the three red, blue group I draw on my front carbon. Right, on the left carbon, we have hydrogen, CH2. On the right, likewise, we have hydrogen, and CH2. So that's CH2 attached to the center of the right carbon. And then you have hydrogen and hydrogen. With me so far? Let's join the Newman projection by looking at what's the connectivity of different carbon atoms. And now let's look at what's in the back. Now in the back, likewise, I'm going to use my green color. For each of the carbon in the back, we have hydrogen, and CH2. So for carbon atom on the back, let's draw the Newman projection and do it this way. Right, on the right carbon, that's the same idea. On the bottom, we have hydrogen, and CH2, I'm holding it. All right? So what we're doing here is simply looking at a chair conformation. You look at it from the side and see, all right, so we do not have any torsional angle because all our groups are staggered over each other. So there's no torsional strand. Ooh, it's a bit hard to hold it. Let me put it down. So yeah, this is what we're doing here. We took a chair conformation, we look at its front view, we measure the bond angle, and we find out that in the cyclohexane, the bond angle is very close to the 109.5, and thus it does not experience any angle strand. All right, so no angle strand because the bond angle in the chair conformation is very close to the 109.5. Now, if we look at the torsional strand here, what we have is all structures are staggered. So no torsional angle. No torsional strand, sorry. All right. How are we feeling here? So that's our chair conformation. So as we were saying, the take-home message here is two pieces. One, cyclohexane in itself is not a planar molecule. It is not a planar molecule because we want to minimize angle strand and also torsional strand. And two, we managed to see why cyclohexane does not have angle strand and does not have torsional strand. especially torsional strand, you can view it by looking at the Newman projection, and you figure, oh, okay, so these groups are all staggered on top of each other. Now this is a better picture to see where that chair comes from. You have one V in the front and one V in the back. That makes their chair conformation. Now your cyclohexane can adapt different conformation. If I rotate this bond here to make it look like a boat, let's see. So your cyclohexane can have other unstable conformation, like a boat conformation. This one is a relatively unfavored conformation. You still do not have any angle strand. Most of the molecule here still have that bond angle around 111 degree. But we can see now all your groups are again eclipsing on top of each other. So a boat conformation is unstable because of that eclipsing of groups. So what I expect you to know, first of all, definitely know how to draw a chair conformation. Know why the chair conformation doesn't have any strand in it. And secondly, if I give you a different conformation of cyclohexane, can you derive, for example, a boat conformation, why this one is unstable? Now, if we look at the eclipsing or the torsional strand in the boat conformation, we can see all groups are eclipsing on top of each other, which explains why the boat conformation is not stable. All right, so let me put it back to my chair conformation. Let's see. The boat again. All right. How are we feeling here? Where's my model kit, by the way? Okay, so it's in the back. So yeah, just pass it around to your friend and classmate and play around with it. And see how easy it is to flip that bond and look at that chair conformation in different perspective to get it right. And again, if you have your own molecular kit, I highly recommend you build a chair and play around with it yourself. If you don't see it as a chair, that's okay. Just know this conformation is conformationally stable and know by looking at the Newman projection why it does not have any torsional strand. Okay? I know every time I say, like, when there is no question, I feel like people are secretly confused about things and don't know what to ask. So I'm going to stay here for another minute for you to dream up a question there. Yes?
Aren't the carbons eclipsed?
Well, so the carbon-carbon bond together, if you look at it, these two are bonded together. Right? When they're bonded together, we don't think they're eclipsed to each other. But these two carbon atoms, they are different position. Now, these two are still staggered to each other. All right? So when we're saying eclipsing, going back to our cyclopropane example, now, if we compare these two carbons and these two, on the right, the cyclopropane is a perfectly eclipsed example. Everything eclipses over each other. But in my chair conformation, in the cyclohexane, they are staggered over each other. All right, so eclipsing is right on top of each other. These two, you can say they're gauche to each other, but they're not eclipsing to each other. Okay. Well, this is actually easier to see. Better than me holding it. Yes?
So does the angle strand on the cyclopropane make it planar?
Yes and no. So in the cyclopropane, you have three atoms that's bonded together. Well, so 3 points define a plane. It must be a planar molecule. It's not because of angle strand. It's because of the chemical bonds together hold these three carbon atoms together as one single molecule. It must be a planar molecule. It's only 3 points, right? You have 3 points that defines a plane, and that's it. Yes?
Can you just go over again where the strand is not in the chair conformation?
This one is given. It's like, I'm telling you that angle is like about 111. this is 1, 1, 1. It's not just some random vertical line. But the normal tetrahedral, you have angle around 109.5. The 111 and 109.5 are really close to each other. That's why your angle strand is minimized. So this information is like provided on the figure. Yes? Again, when we're talking about what angle to use, it depends on the hybridization of your carbon center. Right? When you have carbon that's sp3 hybridized, you're expecting the bond angle there to be around 109.5. Right? So that's back to our lecture 2 or lecture 3 when we talk about hybridization. But if you have a double bond, you're expecting that angle to be about 120 degrees. Or a triple bond, we're expecting that angle to be about, well, 180 degrees. Now, there are several different ways we can ask you a question. For example, let's go back to the ring strand, and I give you a sample question there. Let's imagine our isomers of benzene. Some of the isomers we went over, or you see it in your Canvas assignment, are this 1,2,3 trihexyl triene, 1,2,3 hexyl triene. Now, do we expect this molecule to be a planar molecule, or do we expect this molecule to have a large strand, large angle strand? Right, so the quick answer here is if we look at this hybridization, this carbon here is sp hybridized. This carbon here is also sp hybridized. And what does that tell us? That tells us this molecule will have a huge angle strand because these angles here are definitely not 180. Right, so one of the questions we could ask you about when we're looking at strand molecule is say, now look at this drawing, this chem draw. If this molecule is a planar molecule, do we expect it to have a large ring strand? Do we expect it to have a large angle strand? And that you can get by the way we draw the molecule. If it is planar, then this angle will be super deviated comparing to the 180. These are 120 in the cyclohexyl. Right, but if you're talking about the sp hybridized carbon, they're sp hybridized, we're expecting the bond angle to be around 180. So just a demonstration in what those questions could look like. All right? So back to our chair conformation. Again, we'll keep looking at it so you have more questions. Now the next question comes is how to draw a cyclohexane chair conformation. I'm going to delete these so we can draw it together. So here are some of my personal tricks to draw the cyclohexane chairs. If you have your own trick, use it. Just make sure you know how to draw the cyclohexane chair because you will be using it in future. Now, my personal trick in drawing a chair that looks good is first I use 4 points to define a parallelogram. So when you have two lines parallel to each other. Now, these 2 dots defines the top line, and I want it to be perpendicular to each other. So we can draw it on the left hand, so it's like perpendicular. It's a parallelogram. You also can draw it in the other tilted way, like that. Now, that's coming back to say we have 2 different kind of chair conformation you can draw. But nevertheless, we'll talk about the difference between these 2 chair conformation. We just look at the way we draw it. You first draw 4 dots that defines 2 sets of parallel lines. That's not a rectangle. And then we draw 1 skewed V, connect the top 2 dots. So what we have is like this. And when we're doing that, you can draw 2 parallel, that's the second step. You draw a V shape. Now this V shape is a little bit tilted. It's not your perfect symmetric V shape. It's tilted towards the right direction. That's where the, how do I say it? That's where your parallel lines are tilted as well. And then you draw 2 different parallel lines that connect the left and right. And then what we're doing is finish up by drawing a flipped V. That's going that way. All right, so just keep in mind, we have 3 sets of parallel lines in each chair conformation. This one, these 2 are parallel to each other. These 2 are parallel to each other. And the blue ones are parallel to each other. So when I learned organic chemistry, I used to bring a ruler with me so I can draw my chair really fast on exams. You don't have to do it, like a credit card also works. But these 3 lines are like just parallel to each other, and keep that in mind. Practice it, practice how to draw it on paper quickly. Now let's do that again for the other possible way to draw the chair conformation. So now your dots are skewed to the other direction. So likewise, we draw our V first, and then we connect the lines, and then we finished up. All right? It took me less than 5 seconds to draw it. And you should be able to do that within 10 seconds. If you can't, you'll have some problem in the future in drawing those chair conformation. So practice it until you can do it in like 10 to 15 seconds to draw one valid chair conformation. With me so far? So again, look at that model, draw it, and practice your drawing on the cyclohexane molecule so that you're familiar with it. Now let's coming back to our original question when we initiate this entire discussion. Like why in the low temperature NMR, your cyclohexane gives 2 signals. Remember our introduction picture here? Right? Why at the low energy NMR, your cyclohexane has 2 different signals. So that tells us in my cyclohexane chair, we have 2 different types of hydrogen. Now, what are these 2 different types of hydrogen? In this model here, I used a different color so you can better see it. Now, again, depending on where your molecular axis is, you have 2 different kinds of hydrogen. Now, one of them is going along with the molecular axis, so that is called axial. And these green ones are called equatorial. Let me clear out some space. All right. Now, if we put that into Newman projection, what does that tell us? Now, imagine we're looking at through from this Newman projection perspective. What does this molecule tell me? Again, we're drawing our Newman projection. Let's draw the 2 circles first. Now, the question for drawing the Newman projection is we're trying to figure out, are my red one axial or the white one axial? Now, looking at the Newman projection, what do we have? We have on the here, on the front, we have a hydrogen that is red. And on the side, we have a hydrogen that is black. Now in the middle, we have our CH2. And not worry about that CH2 too much now. And in here, we have hydrogen. And we have the CH2 and the hydrogen. All right, and on the back carbon here, we have the hydrogen that's going out. And we have the hydrogen that's going out this way. And the CH2 is here. All right, so that's how we draw it from the Newman projection. And if we put it back to the normal chair conformation, we can see the red one Now, this is the molecular axis. That's the axis that defines the entire direction of the molecule. Now, your red hydrogens are along with the molecular axis. Your red hydrogen are your axial hydrogen atoms in this chair conformation. So what do we know about axial versus equatorial hydrogens in this case? In this molecule, we can definitely see one difference is you have two CH2 groups that are bulkier than your hydrogen. Now, what does that tell us? By analyzing the relative position, even if they're eclipsing with each other. Now, these axial hydrogens are closer to your CH2 group. And these black hydrogens are anti to your CH2 group. They're away from your CH2 groups. All right, or the other way to put it is your axial hydrogen are gauche to CH2, and your equatorial hydrogens are anti to CH2. There are several consequences out of it. So first of all, in your proton NMR, the reason at low temperature we can distinguish your axial hydrogen versus equatorial hydrogen is because they have different chemical environment. It's not obvious at all if we look at the wedge dash conformation. It is very obvious when we look at the Newman projection. Your anti or your equatorial axial hydrogen, sorry, call it anti for some reason. Your axial hydrogen are gauche to the CH2, and your equatorial hydrogen is anti to the CH2. So in the proton NMR, when your hydrogen sees a different chemical environment, they will show up as a different signal. So that is why at low temperature, you see two different types of hydrogen in your cyclohexane, and those two different types of hydrogen is your axial and equatorial hydrogen atoms. All right? I'm running out of time again, so next lecture we'll spend some time look at the ring flip between the two chair conformation and see how does the substitution on your chair affect the overall conformation. And hopefully we'll have some time look at the biomolecules. We'll see how it goes.